So up next, it's a pleasure to introduce Jim Gatheral, who this is presenting joint work with Elissa Alwas. Well, I'll let you pronounce those names. Those are too difficult for me. And
I'm not sure I can pronounce it. I'm going to say.
Okay. Great.
That's a good name.
And Jim's going to tell us about diamonds and the rough Heston model.
Yeah, thank you, Sebastian. So it's my pleasure today and honor to give this talk in honor of Bruno's 60th birthday. I really thought hard. How am I going to connect diamonds to Bruno's work in the evening one? No, well, you're still in my line. You're still in my line. This is really bad. But I couldn't think of any connection, honestly. But I would like to say that I'm personally very grateful for all the brilliant insights that Bruno has given me, both through his papers and presentations, and also the time that he took personally to help me understand things. So, thank you, Bruno. This is all I could think to connect my talk to Bruno's birthday. Feliz aniversario, Bruno. Did I do it right? Did I do it right?
FAB. No.
FAB. Yeah.
He's 4 years old, so that's a fact.
Okay. So now I'm going to speak a bit faster. I've got 55 seconds less. And forget the outline because this just takes time. So let me start with the two motivations for these diamonds, which are my gift to Bruno now. First is the
Just keep quiet. Just keep quiet. Stand still.
Okay. Tudo bem? So first motivation is the decomposition formula. So Elissa originally came out with a version of this decomposition formula back in 2006, I think, using Maria van Calculus, where she was able to exactly decompose any conditional expectation into two terms, one that depended on the correlation and the other that didn't. And then in 2012, she sort of redid it using Ito calculus and decomposed into three terms. So you can look at the derivation for yourself in a minute, but the formula you end up with is this beautiful thing here. So imagine the H, for example, is the payoff of a call option. Then essentially it's intrinsic, let's just say it's 0, plus is something that depends on the covariance of the log spot, x, and the quadratic variation, m, and something that depends on the quadratic covariation of m itself. So to anyone that knows the Bergomi-Guillon expansion, this looks like Cx psi, and this looks like C psi psi, the first two terms in the Bergomi-Guillon expansion. So why is this formula so beautiful? Well, it's beautiful because it's exact. On the other hand, it's completely useless in some sense because these things, these so-called Greeks inside the formula are pretty hard to compute. You would need to you would need to compute them by solving the left-hand side. Of course, what you can do is you can freeze little s at little t at the initial point, and then you get some kind of approximation. And what Elissa showed was this is, in fact, a small-time expansion. But the point here is that this expansion is this decomposition is exact. Okay. Now, first introduction of diamonds, instead of writing it in the original form, suppose we freeze these now. So we take the s inside and turn it into little t. So we now have these Greeks outside. And as I mentioned earlier, this is a small-time expansion. I rewrite those terms, these Bergomi-Guillon autocovariance functionals, as diamonds. So it's just notation. This dot, which I'm very grateful to Julien for, because this dot represents derivatives. So this dot here represents dx dw. This dot here represents dw dw. How do I know which differential operators the dots represent? Well, I just read it off, right? This is dx dw, dw dw. So now when I make higher order expressions, it's clear what the dot means. The dot means whichever sequence of differential operators is appropriate. Also, please note that since we are talking about solutions of the Black-Scholes equation. So we're talking about conditional expectations of solutions of the Black-Scholes equation, which is this equation. We can see immediately that when H is the solution of the Black-Scholes equation, differentiation with respect to W and differentiation with respect to X commutes, right? So we have no problem with non-commutativity. So we can order them in any way we like. Now, so let's be a bit more formal. Let A and B be semi-martingales. In this particular case, we're only going to be talking about X and M, but of course we can solve other kinds of problems with this notation. Then A diamond B is simply this autocovariance functional. And when A diamond B appears before some solution H of the Black-Scholes equation, the dot is to be understood as representing the action of these differential operators. Now, there's a close connection between those diamond autocovariance functionals and simple moments. So if A and B are martingales, then A diamond B is simply the covariance of A and B. So you're probably at this point getting skeptical. I can see somebody who's looking skeptical, and he's saying, well, you know, what's interesting about diamonds if they're just moments? Well, because sometimes it's easy to compute moments, and sometimes it's easy to compute autocovariance functionals. And we're going to see that for stochastic volatility models, it's much easier to compute the autocovariance functional. It's easy to simulate the moments. So that's my point here. Covariances are typically easy to compute using simulation, and diamond functionals are expressible directly in terms of the formulation of a model in forward variance form. So let's give an example. Here is a solution of the Black-Scholes equation. It's easy to verify. We plug that into Elisa's decomposition formula, and we get the following thing. We get that the expectation of the square of the terminal log spot is given by quadratic variation plus a quarter of the quadratic variation squared minus this diamond functional plus another diamond functional. Now, this, we know that expectation of X is just minus a half W, right? Because that's the quadratic variation, so we take that to the other side. We get the variance of X. We see that the variance of X minus the quadratic variation, which in Black-Scholes is 0, is given by these two diamond functionals, the Bergomi-Guillon CXI and the Bergomi-Guillon CXI, right? So I call this stochasticity. So that's the first application. Define stochasticity to be the difference between the variance of the terminal log spot and quadratic variation, obviously 0 if it's not stochastic vol, and we're only talking about continuous models here, no jumps. Then it's expressible as the sum of these two terms. And again, it's exact for any stochastic vol model. Now, why would this be interesting? Well, if you could somehow extract the stochasticity from the volatility surface directly, then this would be an interesting thing, because how many big T's would you have? Well, in the case of the S&P, I think I showed in my mini course, today we have 35 of these, 35 explorations. And let's suppose our model has 3 parameters, right? Because we only think about rough vol these days. So we have 3 parameters to fit with 35 of these. So in principle, if we could get this from the smile, then we could calibrate our model extremely fast. And it turns out there's a beautiful formula for this, like the beautiful formula in the book, the one that says that the vol swap is simply got by integrating implied vols. I remember this is one of the comments Bruno made in my talk. He said, oh, you basically said, oh, you're being stupid because just let y equal n prime, let y equal n of z, and then you can make this an integral from 0 to 1. That's a good point. So you can make the same comment again, and then this would be like old times. But anyway, I leave it like this because I like to see the kernel. I like to see the Gaussian kernel. And essentially, so you're integrating the whole smile, but instead of a smile with log strike on the x-axis, it's a smile with essentially d2 or d minus, depending on your notation, on the x-axis. So this thing gives you the variance swap. And then we have a very analogous formula for stochasticity. This looks like a skewness of the smile, and this looks like a kind of quarticity of the smile. So is it useful? I don't know yet, honestly, because if you look at the formula, you need very far out of the money volatilities to be able to get a decent estimate of stochasticity. So maybe it's not that practical, but it's beautiful. I'll show you another one of these things that is more practical later. Now, Julien Guillon's name is coming up a lot in this talk, I must say, but it's not deliberate. So following Bergomi and Guillon, let's consider a stochastic vol model in forward variance form. They can all be put in forward variance form, basically. So we have ds over s is sigma dz. It's just Black-Scholes. And to turn it into stochastic volatility model, you write down some specific dynamics for the volatility, right? So, but instead of writing the dynamics on the volatility, you write the dynamics on the forward variance curve. What is forward variance? It's a tradable asset. It's the expectation under the pricing measure of the instantaneous variance at some future date u. So the way they arrived at their expansion was by scaling the volatility of volatility function lambda by epsilon and then setting epsilon to 1 at the end. And they did an expansion up to second order. So our first motivation was an exact decomposition. Then the second motivation is going to be the Bergomi-Guillon expansion. So we just copy down an equation from their paper and rewrite it in diamond form. So we haven't done anything, just changed the notation. But we look at this, and isn't this kind of tempting? You want to write this as the exponential of something. But the exponential of what? We don't know. Well, I'm going to tell you in a minute. So I say here, motivated by exponentiation results in physics, in particular one of my papers, where I show that cross-sections can be expressed, in other words, probabilities of interactions can be expressed as the exponential of sum of connected diagrams. See, notice this is the square of a lower order term. This is the square of a, no, sorry, this is not. This is the square of a lower order term, this one. So it's tempting to say this should be exponential of a sum of connected diagrams, and indeed it turns out to be so. So we look to see if we can do that. So it's natural to represent these autocovariance functionals, they're basically iterated integrals, as it's naturally to represent them using trees, each of whose leaves corresponds to either an x or an m. And we end up with diamond trees reminiscent of Feynman diagrams. Now that we've got trees, why not make forests of trees? And at this point, it's probably completely unmotivated, but you'll see why. So we're going to define our forests iteratively. The first forest, or the 0th forest, is just m, and then the higher order forests are arrived at by recursion. So for example, if we look at here, f1, well, this doesn't contribute because it goes up to k minus 2, is x diamond m, and so on. And so we get a bunch of forests, m, x diamond m, half m diamond m, and blah, blah. I'm going very fast, I'm sorry. And so we can represent these as trees, and they're very much simpler looking than Feynman diagrams, obviously. X diamond m diamond m, and x diamond m. And what are the rules that are analogous to Feynman rules is simply that if there's any symmetry in a subtree, reflection symmetry in a subtree, the tree picks up a factor of half. So here we see a half m diamond m and x diamond m. And to get the tree at the kth order, basically we just count all the trees with k plus 2 leaves, where m counts as 2 leaves. Why does m count as a double leaf? Well, basically because m in some sense is like x diamond x. It's the covariance of x with itself. Somehow, not quite the same. So these are the rules. If there's any symmetry in a subtree, you multiply by a factor of half, and you get the kth forest by just writing down all trees with k plus 2 leaves. For example, here's one tree in F7, and you see you pick up a factor a quarter because you have these two subtrees with reflection symmetry. So why did we construct forests and trees? Well, because this theorem holds. Let H be any solution of the Black-Scholes equation, and then just like the Alice decomposition formula, we have this exact decomposition here. That this solution is given by the exponential of a sum of forests defined using that recursion formula acting on H. And the dot, what does it mean? Well, whatever is in the forest, right? So each tree in each forest has a different, corresponds to a different sequence of differential operators. Now, what's the most interesting solution of the...
Is this somehow related to Trotter-Kato formula?
I'm sorry?
Is this related to Trotter-Kato formula? For
I don't know this formula, but your question is the latest in a long line of similar questions. You know, like somebody says, oh, this looks like Edgeworth expansion. I think he's right. Another guy says this looks like stochastic Taylor expansion. I think he's right. Another guy says, oh, this looked like Baker-Campbell-Hausdorff. I think he's right. Right? Okay. So I think they're all morally equivalent. But except here we have an exact formula, and we can write down all the terms directly from the formulation of the model in forward variance form. So what's the most interesting solution of the Black-Scholes equation? I would say the Black-Scholes characteristic function. Well, so I claim, and I hope you'll agree with me. So if we act with the exponential of sum of forests on the Black-Scholes characteristic function, then each of those f dots turns into a number, f tilde of a. Each time we take an x derivative, we get a factor ia. And each time we act with an m derivative, we get a factor a half a plus I. Then it's direct from, it's just a corollary of the theorem that now we have an exact expression for the cumulant generating function, which is defined as the log of the characteristic function. So we have that the cumulant generating function is just the Black-Scholes piece, which everybody recognizes, plus a sum of forests. So this is true for any stochastic volatility model. So now we have a characteristic function for any stochastic volatility model. Well, you say, okay, yeah, but you need to compute all the trees, and maybe they get hard to compute, and so on. But much of the time, we just want to compute moments, and then we only need a finite number of these terms. And I'm going to give an example where we can actually sum a subsequence up to infinity. So here goes the example. The variance swap, which is kind of trivial, is got by taking the first derivative of the cumulant generating function evaluated at 0. Okay, so we get the standard thing. It's just minus a half times the quadratic variation. Boom, boom. That's the expectation of the log spot. And what about the gamma swap? Well, it's the entropy contract. We do a similar thing. And it's the first derivative of the cumulant generating function evaluated at minus I. Now, let's think about that. Each time we take a derivative with respect to m, we have a factor a half a plus I. And a plus I, if a equals minus I, is 0. So basically, all these terms fall out. You get left only with trees that have only one m leaf. And so we end up with this expression for the leverage swap, which is the difference between the, well, actually, only trees containing a single m leaf will survive in the sum after differentiation, so that this is given by that, where what do I mean by this? I mean x diamond m plus x diamond m plus x diamond m, and so on forever. So you add all of these up, and you get this beautiful expression for the gamma swap. Now, the leverage swap, which is interesting product, presumably traded, because gamma swaps are traded and so are variance swaps. Leverage swap is just the difference between a gamma swap and a variance swap, and you can see this is the variance swap, this is the gamma swap. So now we have a very elegant expression for the leverage swap. And I'm rapidly running out of time. Okay. So can we get leverage swap from the smile? Yes, it's easy. We know how to get gamma swap from the smile, and we know how to get variance swap from the smile, and this is actually very practical. So I'm going to skip that. I talk about how beautiful the Bergomi-Guillon expansion is, and we can extend this expansion to all orders up to infinity. I don't know how useful that is. You go to the first couple of terms and you see, oh, this is beautiful, the leverage swap is emerging, but then you got all this junk. So one can do it, but it's not clear that it's interesting. So now let's skip to the rough Heston model, which, as I mentioned yesterday, for those of you who are here, is the most tractable stochastic volatility model known to me, at least. Certainly more tractable than the classical Heston model. And all these things are eminently computable in that model. So these are the dynamics. And in forward variance form, this is the dynamics of the rough Heston model with mean reversion set to 0 because there's no need to have mean reversion. Writing conventional Heston or classical Heston in forward variance form, we see that all we've done is we've replaced the exponential kernel in classical Heston with a parallel kernel in rough Heston. Now everything becomes easy to compute. We can compute dx, that's obviously just Black-Scholes. We could compute dm, it's this thing. And then we find that we keep having integrals of that form to compute. Well, f1 is this expression. We keep finding integrals like this, so we define them. We compute the dynamics of that integral. We get this. And then with that notation, we see that x diamond 1, which is the first forest, is proportional to I1. And then we see that there are two trees in forest F2. They're both proportional to I2. But notice we're seeing a pattern already. See, this is x diamond m. This is x diamond m. And we very quickly recognize the pattern. X diamond to the power k gives, right? So we can sum up all these terms. This is a very simple infinite sum. So we sum up all these terms to get the leverage swap. And we now have an exact expression under rough Heston for the leverage swap using Mittag-Leffler functions, which is kind of cute. Now, is it useful? Yes, it's very useful because, well, now I'm going to normalize because it seems natural to normalize. This looks a bit like if this were constant, this would come out front, and then this would give me variance swap times something. So I normalize, and I get this formula for the normalized variance swap, assuming I have a constant forward variance curve. And then I can calibrate, basically. Well, here's an example of how quickly that sum converges. This is just using one forest. This is using two forests. This is using three forests. And the red line is the exact solution. So we basically got extremely rapid convergence of the leverage swap. So in practice, we can use this for super fast calibration of the rough Heston model to data. And I'm going to show you how it's done in practice. So I'm using these curves from a private company called Voladynamics. It's Tim Klassen's startup, where he's basically taken some SVI-style curves. SVI, as I mentioned yesterday, doesn't fit anymore. Was it yesterday or the day before? My memory is short. Was it yesterday? So anyway, SVI has too few parameters to fit the smile these days. It used to fit back in 2011. Even 2012, but it doesn't fit anymore. So I use these 13 and 14 parameter curves and ask, well, is the robust estimate of the leverage swap, does it depend on the curve? Well, the blue points and the red points are the estimates from the two curves. We can see that indeed the estimates from the market do depend on which curve you use because the extrapolation is different, but they don't depend too much. And you get pretty robust estimates of the parameters of the rough Heston model, good enough for practical use. And even with my bad R code, its calibration takes like 0.02 seconds. So in summary, and I think I'm going to finish on time, unbelievably, we stated the ALOS decomposition formula, beautiful formula, but probably not that useful. We introduced diamond notation. We defined trees and forests and showed how to compute all such forests diagrammatically. So in it, one of the corollaries is that we have closed form characteristic function in principle for any model, not just for affine models. And we used this theorem to compute various quantities of interest under the rough Heston assumptions in closed form. And in passing, you saw how beautifully easy things are to compute under in the rough Heston model. And with that, I'm very happy to take questions.
So indeed, we do have time for questions. So who'd like to start?
I think that's the fastest I ever spoke. 50 slides in 25 minutes.
Yeah, you had an extra
Hi,
6
Joseph.
minutes, basically. Sorry?
Sorry, what kind of algebra? I'll repeat the question, sorry.
So trees and forests appear, for instance, in the theory of branched rough paths. And there the algebraic structure plays a big role, which is reminiscent a little bit of what you're doing. So does this algebraic structure also play a role in your theory?
Well, you're asking the wrong guy, but once again, your
I
question
think
is
you're
in a long line of similar questions. Other smart people have said, oh, this reminds me of regularity structures.
Yeah, branched rough paths more directly.
Yeah, so Claudio Tebaldi has told me that he is close to figuring out which algebra this is.
Okay.
So he's obviously asked himself the same question. I'm excited to see the result.
Very beautiful. And the second little question, you said that rough Heston can be better calibrated or estimated than Heston. What did you mean with that?
Oh, I didn't actually say that, but it's true.
I was
so in other words,
extrapolating.
if one were to draw the leverage swap term structure for classical Heston model, what you would see, I don't know if you can see the laser dot here. I can't see the laser dot. Can you
We
see
can
it?
see
Where
it
is
here.
Where? Oh,
It's
here,
the
here,
distance
here.
which makes
So
it.
it would look something like this. Then it would go flat.
Yes.
I would go down here, maybe it would go flat. So it's completely inconsistent with the shape that we see
No,
here.
this I understand. I understood it numerically that you can do more with rough than with others.
Yeah.
No. This
In
is
other
the
words,
same.
it fits the points that
Yeah,
we observe.
okay, I see.
And then in terms of speed of calibration, it's just because we have a closed form formula, right? It's super fast to compute.
Okay.
And we only have 3 parameters and 35 data points, right?
Yeah. Thank you.
Other questions? I think JP has one here.
Thank you. So this formula doesn't remind me anything, but, but I want to ask you.
But Jean-Pierre, is that good or bad?
No, I think it's good. But you have this infinite series.
Yes.
Can you prove convergence, or
I'm sorry?
can you prove?
Oh yeah, this is another standard question.
Yes, of
No,
course.
no. I mean,
Oh.
all these results are formal. Convergence of subsequences, like this one here, well, this is convergence by picture. Actually, it's easy to prove convergence of this thing. But there are other things. For example, the Bergomi-Guillon expansion, for sure that doesn't converge. It diverges everywhere. There may be, I conjecture, there may be some magic point at which it converges, but I haven't found this point. Everywhere else, for sure, it diverges.
Any last one quick?
George was
George has
wanting
one.
to
Okay,
ask something.
yeah.
I mean, it's so isomorphic to the expansions of quantum mechanics
Right.
that
Of course, yeah.
either it's Heisenberg algebra or it's some kind of algebra that you cannot explicitly explain because it's just infinitely generated. So
I believe in Claudio. He's going to tell me the answer.
Okay, with that, let's thank Jim once again.
Thank you.